네, 감사합니다. 네, okay. Hello, everyone. Good morning. My name is Won-Chul Shin, and I'm a master student in Choice Group. Okay, let's get started. Today, we're gonna implement Bert, the sensational model in NLP. Yeah, Bert's architecture is a set of the transformer encoders that we've learned last week. While pre-training process, Bert performed two unsupervised tasks: next sentence prediction and mask language modeling. We will implement all of this. Here is today's contents. First, we will implement Bert from scratch. I'll show you the whole pre-training process from scratch. And then we will perform downstream task, which is sentiment analysis. Actually, you don't need to build your BERT model from scratch like section 1, because there are verified BERT library from Hugging Face. So we will use Hugging Face library for the section 2. Okay. First, import required libraries. And download the sample corpus. Yeah, I have already processed the corpus so that it can fit into the model. So you can just download by running this cell. Yeah, our corpus should be prepared with 2 tokenized sentences in one line with this separator. This is our sample tokenized.txt file. If you open this text file, you can see this. Tokenized sentence 1 is here, and the separator, and then tokenized sentence 2 is here. Yeah, 2 sentence is connected with this separator. So our code will recognize this separator and split the connected sentence into 2 sentences, and then split each sentence into tokens based on this blank space. Yeah, split all the tokens based on this blank space. So yeah, we can see this process in the code below. Okay. Next, making dataset for pre-training. I can't explain every single line, so I'll just explain the crucial point. First, let's see the vocab class arguments. Counter is holding the frequencies of each token found in the data. And max size is the maximum size of the vocabulary, and min frequency represent the minimum frequency needed to include a token in the vocabulary. Specials represent the list of special tokens like shared as token. Okay, the crucial point of this class is building I to S and S to I. I to S means I means index, and S means represents string. Yes. So I to S is a list of token strings indexed by their numerical identifiers. This is sorted by frequency, then alphabetically by this code. And S2I is a dictionary mapping token strings to numerical identifier. Yeah, you can just think this the reverse version of I2S. Next, word vocab class is a parent class of vocab. Here, text arguments will be our text file. So from here, we will read our text file line by line and split by blank space. And make counter object, which is holding the frequencies of each token. This object will go to the child class. Yes, child class. Okay, that's it for the process of building vocab. Let's run this code. 뮤트 어려. 네, 감사합니다. Oh, so okay, done this. We can print special tokens. We can print special token like this. Yeah, pet token index is 0 and mass token index is 4. And also, you can see the vocab made. If you run like this, 5 index represents the token the. Also, you can find the index I2S. Okay. I2S is the vocabulary. You can find if you put the index and I2X, I2X get the tokens. So if you run like this, you can show the all vocabularies. So as I said, I2S is a list of token strings indexed by their numerical identifiers. Yeah. Yeah. Index 0 represents pad. Yeah. Index 1 represents U and K, like this. Okay. Okay, next, we will create a PyTorch data set. Here, sequence length means the maximum length we set. When this is done, self-lines looks like this. It's a list containing the sentences of our corpus. Okay. Anyway, let's go to get item method here. If you call this random sent function, we can get items row sentences in the corpus, but the second sentence is randomly replaced. Let's see this random sent definition. Yeah, at 50% probability, the second sentence is randomly replaced and the label is 0. From Jisoo John, what was with sharp sharp are this came from the tokenizer. Yeah. If you are not familiar with byte pair encoding or word piece or sentence piece tokenizer, I recommend you refer to the last week lecture materials or Bert lecture materials. Yeah, there is explanations of sharp byte pair encoding or tokenizer, so you can understand the sharp characters. Yeah. Yeah, so I explained random send function. And then, so T1 and T2 types is string. Is next label is 0 or 1. 0 means randomly changed pair. And 1 means 1 represents correct pair. And if you call this random word function, let's see the random word definition. Yeah, here. Our training data generator choose 50% of token positions at random for prediction. 80% of them are changed to the random token, and 10% of them will be remain as same. No. 10% of them are changed to random token, and 10% of them will be remain as same. Yeah, remain as same, but need to be predicted. Yeah. So if you put string T1, then we will get T1 random, which is T1's token index sequence with some mask tokens. And T1 label is holding the answer label of tokens to be predicted. But T1 random does not contain CLS SCP index yet. So we add special tokens at the front and back of the sequence in the next line. So yeah, also we pad the remaining length. So final length will become a sequence length which we set. Yeah. So the final output is dictionary containing Bert input and Bert label or segment label is next. It's okay if you are not sure what this means. I will show you this code implementation below for your understanding. 예, 김재균님 질문이 15% 확률로 마스킹만 하는 게 아니라 왜 랜덤 워드도 넣고 기존 워드도 냅두나요? 15%의 확률로 이제 모두 마스킹 하는 게 아니죠. 제가 지금 보여드린 게 모두 다 마스킹 토큰으로 바꾸는 게 아닌데, 그게 이제 뭐 글쎄요, 버트 논문 저자들이 좀 더 로버스트한 모델을 만들기 위해 이렇게 하지 않았을까 생각이 됩니다. 네, 제 생각에는. 네, 저도 그냥 수동적으로 받아들였어서. 네. 근데 재균님이 설명하신 게 맞습니다. 네. 15%의 확률로 모든 걸 다 마스킹하는 게 아니라 어떤 거 그중에 80%만 마스킹되고 그중에 80%만 마스킹되고 뭐 그중에 10%는 랜덤하게 체인지하고 그중에 10%는 그대로 냅둡니다. 네. 제가 15%를 제한 85%도 그대로인. 아, 그렇죠. 네. 85%는 그대로겠죠. 그 85%를 보고선 15%를 맞추는 거죠, 소장님. 네. 오케이. 잠시 물 좀 마시겠습니다. Okay, I prepare this for your understanding. If you run this cell, we can get the length of data set, and we can get the first data point like this. Yeah, as you can see, Bert input means sequence of the two sentences. Yeah. As I said, 3 is CRS token and 2 is the SCP SEP token. Also, 2 is here, yeah, because sentence 1 SEP, sentence 2 SEP. Yeah, this Bert inputs. The whole length is 128. Why? Because we set the sequence length arguments 128. 네, 전민님, 경민님, 네, 추가 설명 감사드립니다. Okay, and Bert label means the answer of positions to be predicted. Yeah. All positions that do not need to predict it are padded to 0. Also, there are segment label and is next label. Is next label is 0 or 1. 0 represents not correct pair, and 1 represents correct pair. Okay. I hope you guys understand the dataset format and move on to next part. Building the Bert model class. Next part is building the Bert model class. We've already learned the transformer last week. Bert used transformer encoders. That's it for Bert architecture. Here are attention and multi-head attention, sub-layer connection, and position-wise feed forward. Yeah, actually we already learned all of these classes. Self-attention is multi-head attention, and sub-layer connection represents this line. Layer norm is implemented in here with sublayer in the sublayer connection class. And position-wise feedforward represents this. So in the Bert paper, this is the Bert paper, they use a Gallo activation rather than the standard ReLU following OpenAI GPT. Yeah, so I use Gallo activation function in the position-wise feedforward class. Actually, I don't know the theoretical background why they use Gallo. I think this is an empirical finding. Yeah. Anyway, all of this is in the transformer block. It's same part with last week's session, so I won't explain them. If you are not familiar with transformer architecture, refer to last week's lecture materials or ask transformer TA. 실행을 안 시키고 갔네요, 제가. 야, 여기까지 가면 안 되는구나. 네. Okay, I'll explain the Bert embedding. Yeah. As you can see, Bert embedding consists of token embedding, segment embedding, and position embedding. Yeah, we've already practiced token embedding and positional embedding last week. So segment embedding is here. It's not difficult. Here is 3. Why 3? Yeah, it's easy. Yeah, here is the answer. We have 3 indices, 0, 1, and 2. Like this. Segment label has 3 indices, 1, 2, and 0. So here is 3. Okay, let's see here, Bert embedding class. Vocab size argument represents total vocab size, and embed size argument represents embedding size of token embedding. And I made a quiz. Here is quiz. Make Bert embedding using token embedding, position embedding, and segment embedding. I'll give you 5 minutes. Think of this picture. Yeah, we made Bert embedding by adding or, not concatenating. 네, 이거 이름이 없으신데 유저님께서 말씀하신 것처럼 그때 저희 트랜스포머에서 배웠던 지난주 강의 시간에 배웠던 사인 코사인 막 계속 바뀌면서 인베딩 줬던 거 있잖아요. 네, 그겁니다. 네, 같은 겁니다. 완벽히 같은 겁니다. Okay, let's fill in the blanks together. Yeah, I copied from my answer sheet. Yeah. Yeah. We need to add all of them. So just adding token embedding and position embedding and segment embedding. Their shape is batch size. This shape is batch size by sequence length by hidden, and this shape is 1 by sequence length by hidden, and this shape will be batch size by sequence length by hidden. Yeah. Okay. Okay, we are ready to build the BERT model. The arguments are vocab size, hidden size, and number of layers, and attention head, number of attention heads. Yeah. This default spec is BERT base spec. So the code below is same with transformer encoder. Yeah, just tag of multi-head attention layer. Okay. I prepared this cell for understanding the input and output shape of BERT. First, make a BERT instance. If input shape is 2 by 10 like this, what is the output Y size if input X is like this? Let's think about it first and check it by run the cell. If you're done with this, try the bottom one. Calculate the number of parameters of BERT above. Yeah, this one. Calculate the parameters of that. I'll give it some time. Oh, someone got the answer. Yeah, I'll give you 1 minute more, 1 minute more. Okay, let's fill in the blanks together. Yeah. I will wait some time. Did you copy it? Yeah. If Bert input of Bert is Rx and segment label, so you can get output. Let's run this cell. Yeah. As you can see, X's shape is 2 by 10. 2 means batch size, and 10 represents sequence length. The output shape is 2 by 10 by 768 because we set hidden size 768. I hope you understand the shape of input and output of Bert. Okay, and for the next answer, yeah, R-based, yeah, copy it. Yeah, did you or copy it? Yeah, okay. If you run this code, total parameters is 106 million. Yeah, we defined, Bert defined above has Bert base pack. In the Bert paper, the author said Bert base has 110 million parameters. Yeah, we made Bert model instance with same number of layer and same number of attention head, and same hidden size. But the number of parameters are slightly different. Why are the number of parameters slightly different? Yeah, one thing is different. The answer is the vocab size is different. The Bert base use 30,000 tokens, but we use 27,000 tokens. If this is reflected, the number of parameters are close to 110 millions. Yeah. Okay. Now it's time to prepare for the training. Bert Adam class perform Bert Adam, yeah, Bert Adam. Bert Adam class perform next sentence prediction and masked language modeling. Let's see the fourth method first. X and segment labels shape will be batch size by sequence length. And the output of Bert has batch size, sequence length by hidden size. Okay, this output is used for next sentence prediction and masked language modeling. I explained the process, so now please fill in the blanks in the NSP and MLM class code below. you have to think that we use the first token, CLS token, for the next sentence prediction. CLS, CLS tokens. The first token of our input, the input. This 3. Okay, let's fill in the blanks together. Here is, and then dot linear hidden 2. Why 2? Because we are doing binary classification. Yeah, is next or is not next. Yeah, we are doing binary classification. So here is 2 and softmax for making probability. And that softmax dim -1. -1 means do the softmax operation along with last dimension. So plus return self dot softmax self dot linear 0. Yeah. Why? Why 0? Yeah, we have to use the first token for the NSP. We have to use the first CLS tokens embedding vectors for NSP. Yeah. And next, here is, and then the linear hidden vocab size. Why vocab size? We have to predict one token of 27,000 tokens. 지수 John, you can do that. Yeah, that's right. 소프트맥스 결과를 CLS 어디 갔지? CLS 소프트맥스 결과를 CLS와 비교하는 것 아닌가요? 소프트맥스 결과를 그게 무슨 말씀이시죠? 소프트맥스 결과를 CLS와 비교하는 것 아닌가요? 자, 이게 이제 그 X가 벌트를 통과하고 나온 배치 사이즈 바이 시퀀스 렌 바이 히든 이잖아요. 근데 지금 시퀀스 랭에서 0번째, 그러니까 첫 번째 768자원짜리 벡터를 가지고 왔다는 거죠. 이게 즉 이 사진에서 여기서 그러니까 여기 지금 벌트가 인풋이 다 이렇게 들어가면 요 토큰마다 벡터 768차원짜리 히든 사이즈짜리 벡터가 나오는데 그 중에 요거를 지금 가져왔다는 거고 그거를 2차원으로 768차원을 2차원으로 줄이는 작업을 한 거고 그리고선 소프트맥스를 취해가지고 확률처럼 만들어준 건데 지수님께서 말씀하신 것처럼 저렇게 그냥 1차원으로 줄이고 시그모이드를 해도 됩니다. 네. 네, 좋습니다. And next, here nn dot softmax dim minus 1. And here self dot softmax self dot linear x. Yes, John, you are right. Yeah. Yes, because BC, I think will be BC loss using sigma classifier. BCL 로스는 그 소프트맥스가 포함이 되어 있잖아요. 네. 그래서 맞는 얘기이신 것 같습니다. 네. Yeah, okay. Let's run. Okay, let's go to Bert trainer class. here are many arguments, but many of them are for optimization. Set up CUDA device for Bert training and make Bert instance and initialize the Bert language model and set the train and test data loader. But actually we don't have test data, so ignore this. And then set the Atom optimizer with hyperparameters. And I use negative log likelihood loss because I manually do the softmax operation above. Yes, so I used negative log likelihood loss. But you, here ignore index 0 means we don't need to predict the not masked tokens. That means we have Bert label like this, and our model don't need to predict zero tokens, zero positions. Yeah, our model needs to predict only not zero positions. So what is it? And then in the next sentence prediction task, we are doing binary classification 0 or 1. So you can't ignore 0 index. So I didn't write like that. And then when you see the iteration function, it's a canonical process for training. Yeah. So just calculate the next loss and mask loss and sum of them. The final loss is this. So like it's just canonical process. So zero grad and call the backward and then call step like this. I hope you are familiar with this process. So yeah, we are almost at the end. Let's define a train function. I define the train function using the Bert trainer. So load vocab and load the train data set and then create data loader and build Bert model and do the training using the Bert trainer. So that's it for the modeling Bert and pre-training Bert. Yeah, you can see the loss. I run, if you run this code, it takes long time, so I won't run this there now. But if you see the if you see this screen, you can see that loss is decreasing. Yeah. This takes a long time, so yeah. I won't run this cell. Actually, I didn't do any preprocessing, and I didn't use optimization techniques, and I didn't search the hyperparameters. The goal of this code was just to show the process of pre-training Bert from scratch. I think the practice up to here was enough to make you understand Bert. If you need to do pre-training or fine-tuning Bert, just use verified library from Hugging Face. You don't need to build the Bert from scratch like me. Okay, next section. Section 2 is sentiment analysis with Bert. Yeah. From this section, I will use transformer library by Hugging Face, and I just used the pre-trained Bert. Yeah, so first, install transformer packages. Okay, and then import required libraries. Okay, and download the dataset. This is the Google Play app review dataset. Oh, there is my mistake. Delete this part. This dataset is not same with the section 1's dataset. Yeah, that's different dataset. That is my mistake. Okay. Yeah. As you can see, the dataset has score and review text in text column. Yeah, we use two column. Yeah, we will use two column. So dataset shape is, we have 15,000 data point. So we're gonna to convert the data set into negative, neutral, and positive sentiment. So if you run this, yeah. I defined two sentiment function. It makes data set with 3 classes. So if you plot the distribution, you can find, you can see this. Yeah, the balance was mostly restored. Okay, let's pre-process the raw data. You need to convert text to number. Tokenizer, so you can just download. And then let's use this sentence, this text to understand the tokenizer process. Yeah. Sample text, I give nice to meet you, how are you, like this. And if you run this cell, yeah, our sample text is here, and the tokenizers from Hugging Face automatically split and make tokens. So token here, tokens nice to meet you. Dot how are you? Yes. And token ID is here. Also, you can see the special tokens. 102 means represents SAP tokens, and 101 represent CLS token, and 0 means pad. Also, 100 means unknown, UNK. All of that work can be done using the encode plus method. Tokenizer.encode plus and put the target sentence is string and truncation through max length 32. Max length is the sequence length above section 1. Just same meaning. And add special tokens true, return token type ID first, path to max length true. That means path 0 with path 0 to make a length of 32. So if you run this, you can see that length is 32 and the sequence of tokens. Attention mask has the same length. 1, 1, 1, 1, 1, and 0, 0, 0, 0, 0. We can invert the tokenization to have a look at special tokens like this. Convert, the method is convert IDs to tokens. Okay. Bert works with fixed length sequence, so we will use a simple strategy to choose the max length. If you plot the distribution of length, you can see this distribution. Most of the reviews seems to contain less than 128 tokens, but yeah, I'll choose the maximum length of 160. Yeah. Now we have our building blocks required to create a PyTorch dataset. Yeah. So you can easily make your own dataset class. Yeah, returning review text and input IDs and attention mask and targets. Yeah. For your understanding, I prepared some code. If you run this code, the length of data sets is 15,000, and first data point has first data point original review text is here, this, and input index containing the sequence of tokens, and attention mask containing 11111 and 0000 of length of 150. Truncation true. Yeah, I did. if you if you put these arguments true, as Jisoo said, yeah, the error message will be removed. Okay. Okay, and split the data set. Shape is here. And create data loaders. Yeah, I create train data loader, validation data loader, and test data loader. Let's have a look at an example batch from our training data loader. I use 16 batch size. So if you run this code, yeah, we have 16 samples because we set the batch size is 16. Okay, you can download. 160은 그 여기 그 맥슬란을 저희가 160으로 줬을 거예요. 네. 벡터 차원입니다. 벡터 차원이 아니죠. 벡터 차원이 아니죠. 죄송합니다. 벡터 차원이 아니고 시퀀스 랭스입니다. 네. Okay. And let's download the Bert, pre-trained Bert from Hugging Face. From Roshda, I also run the code with truncation first, but nothing happened. You can just do with truncation first. Just pop up the warning message. You can just ignore. Usually, you can ignore the warning message. If you give max length properly, that works well. Yeah. Okay. So let's try to use our sample text. Yeah, our hidden size is 768 by default. The Bert model by Hugging Face, we need we can get two outputs. One is this, and the other is the last hidden state's first token, and then linear layer and do the tanh operation. Yes, I mean, do you understand what I'm saying? Yeah, we are doing sentiment analysis, so we have to use pooled output. yeah. 네, 한국말로 하자면요. 허깅 페이스의 벌트 모델에 인풋을 넣으면 아웃풋이 두 개가 나오는데 이거는 저희가 여태 봤던 그 아웃풋이고 하나가 추가적으로 나오는데 이거는 맨 앞에 토큰, CLS 토큰의 벡터, 임베딩 벡터입니다. 근데 그것만 그냥 뱉는 게 아니고 뭐 한 번 리니어를 태우고 그 다음에 탄H를 거친 그런 게 아웃풋으로 하나가 더 나옵니다. 네, 그래서 만약에 32는 아마도 32가 그 저희가 위에서 샘플 텍스트를 만들 때 이 샘플 인코딩이라는 객체 오브젝트를 만들 때 이 샘플 텍스트 Nice to meet you, how are you 라는 샘플 텍스트를 넣어서 인코딩을 만들었잖아요. 그때 맥스 랭스를 32로 줘서 지금 이 인코딩이라는 객체, 그러니까 딕셔너리의 인풋 인덱스를 찍어보면 32길이짜리가 나옵니다. 지금 이 텍스트, 샘플 텍스트 가지고 한번 허깅 페이스 벌트 모델에 넣어본 거거든요. 그렇잖아요. 지금 인코딩을 넣었잖아요. 요거. 네. 그래서 지금 시퀀스 랭이 32가 된 겁니다. 이따 밑에서 보겠지만 이거 그냥 다 설정하시면 되는데요. 그래서 디폴트로 768차원짜리 벡터가 나오는 거고요. 맞습니다. 72 중 하나가 CLS인 겁니다. 맨 앞에 게 CLS인 겁니다. 그래서 그냥 여기서 맨 앞에 거 가져다가 그냥 내가 마음대로 가공하면 됩니다. 굳이 이거 안 쓰셔도. 근데 허깅 페이스는 친절하게 아웃풋을 두 개를 뱉어주더라고요. 그래서 이 벌트에다가 인풋을 이렇게 인풋 시퀀스 인덱스랑 어텐션 마스크를 넣어가지고 아웃풋을 뱉을 텐데 그걸 두 개를 넣어서 받아줘야 되더라고요. 네. 그래서 그냥 저는 이걸 썼습니다. 뒤에 보시면 아시겠지만 어차피 저희 맨 앞에 CLS의 인베딩을 쓸 거기 때문에 네, 그렇습니다. 네, 그 얘기를 지금 써놓은 거고요. Okay, and then I define sentiment classifier which has linear layer. Note that linear layers dimension size. We are classifying three classes: neutral, negative, and positive. So here will be three. Yeah, like this. Len class name is 3, so model class 2 device. 이거 안 해. Yep. And we'll move the example batch of our training data to GPU. 16 is batch size, and 160 is sequence length. Yeah, to get the predicted probabilities from our trained models, we'll apply the softmax function to the output. Yeah, from here, you can easily because I wrote down the text kindly, so doing yourself from here. And train takes some time, so I won't run the training code. Yeah, that's it for the today's class. If you fine-tuning the dataset. Oh, if you don't want to wait, just download my train model. I uploaded my Dropbox, and you can just get the model. So if you do the evaluation, you can get if you do the evaluation, you can get 89% of accuracy in the test set. Yeah, our model will be well generalized. You can see the you can plot the confusion matrix also, and also you can predict on raw text. Yeah, if you well, not bad, will be the model will predict neutral. Yeah. So that's it for the Bert practice. Yeah. The references here. Yeah. It's pretty long and complicated. Yeah. So I hope you guys to study alone slowly and understand the whole process of training Bert, pre-training Bert, and building the Bert model. Yeah. Thank you for listening. Do you have any questions so far? Pulled output. Okay. Pulled output is I wrote down here the last vectors of first token, that means CRS. Yeah, from this CRS, vector from this CRS, and do the linear operation, and then do the tonnage activation function. So it's just first vector with some operations. First tokens vector. Do you understand what I say, Rashda? Why? Why do we need? Because we are doing class, because we are doing sentence classification. We are doing text classification, especially sentiment analysis, classifying neutral or positive or negative. So we need a compressed information of whole sentence. So we have to use one of these vectors. For example, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 vectors came from Bert, but which one is proper for the information of whole sentence? I think, and many people think, the CRS tokens vectors from CRS token will let's use CRS vector from CRS for the sentence classification. Yeah. Yeah, right. Okay. Do you have any questions? 질문 없으시면 여기서 마무리할까요?
네, 오늘
네.
다 끝나신 것 같은데. 네, 그렇게 하시죠.
네, 감사합니다. 네, thank you for
Alright.
listening.
Thank you, TA 원철, and I'll see you guys next Tuesday.
Okay, bye bye.
Bye-bye.